So we're going to continue our discussion of fifth postulate within the how we can define how in hyperbolic plane geometry. So we assume that from given point to a straight line, there can be more than one parallel lines which can be drawn. And accordingly, what sort of geometry which we can construct in that hyperbolic plane. So this is going to be our topic of today's class, or we can say geometry of hyperbolic plane. I can say geometry of hyperbolic plane within the context of our previous understanding of fifth postulate, or Euclidean formulation of the fifth postulate. So what we are going to do this fifth postulate means we are going to have a characteristic postulate of characteristic postulate of hyperbolic geometry and its consequences, which we can consequences of this postulate which we are going to study. So for example, the postulate, if we are going to state the postulate states that, so which is again a restatement of the fifth postulate, which we might have studied, tried to prove, or tried to prove it, not disprove it in different cases. And if we postulate it within this context, the postulate is that through a given point, not on a given line. So not on a given line. So through a given point, not on a given line, more than one line can be drawn, not intersecting the given line. So what we are assuming that, so what the postulate states that through a given point, not on a given line, more than one line can be drawn, not intersecting given line. So through a given point, not on a given line. So through a given point, not on a given line, there more than one line can be drawn, which is not intersecting that given line. So this is another way of stating the fifth postulate. So what the consequences which we can draw from this very supposition is that if I first draw the diagram to just illustrate or emphasize the point that if we take a point P, so if it's a point P, so from the point P, you can assume, for example, you can draw one of the lines which can be drawn E, F. Now you can have not one line. So normally we assume that from one point you can draw one point which one line can pass through a given point, which is assumed parallel to the plane, which is Euclidean thing. Now from this point which we had previously also constructed, many lines can be drawn, equally parallel lines can be drawn to this given line. So if you draw those parallel lines accordingly, for example, we can draw AB. So So not for the sake of clarity, I'm going to just rub off this postulate so that my diagram can be become more visible without tincturing with the basic statement of the statement of the this postulate. So what we are going to say, so if this is one line, so you can draw many lines which can be parallel. So one of the lines you can draw is AB, another you can draw is CD. So you should assume that these lines don't intersect. So this line, if extended, it's not going to intersect this line, neither is this line going to intersect this line. So it's assumed that still it will be parallel. That's the point. So what's the construction? So if it is this, or in the same way, we have another line from this, which is this drawn, which is OR, and again another line which is S. So you can say, you can from this point you can have an equiangular line S from both segments you can draw. So if you draw PA from this side, you can draw PD from this side. If you draw EF, PE from this side, so you can, if you join them, they can construct one line. So you can have equiangular line segments from the both sides of the point, and you can draw as a construction. Because once this line is going to go this way, so this is a construction, and from this point you can have height H, you can have point Q. Yes, this is this. So again, if we have this is S, this is S. So you can have other lines like K, G, H. So G, this is I. Yes. So this is these are different points. So this is line L on which we are having this construction. So now what's the point? The point is like this. So if there is more than one line through a given point not intersecting the given line, there is an infinite number of them. If P is the given point, so if P is the given point, L is the given line, L is the given line, and AB and CD, two lines through P, AB and CD through lines through AB and CD through lines through P which do not intersect L, then no line such as EF, lying with the vertical angles APC, APC and DPP, which do not contain perpendicular PQ from P to L. So they do not contain a sort of perpendicular from P to L. So you can, from these parallel lines which are being constructed from this point, which from an Euclidean perspective, these lines shall intersect this line. But from a fifth postulate, another way of looking at fifth postulate is that through a given point more than one line can be drawn which is parallel to the given line. So these can be different angular, this point can have different angles vis-a-vis, different angles can be drawn, but there's only one point Q from which this line can be drawn, which is assumed to be perpendicular to that Euclidean line. So other lines can have angles, slant of the angles, which may or may not, which not necessarily be 90 degree. Only there's a one point in the line where so you can have a Euclidean picture. It can be generated from that. So PF is perpendicular to PF as well as PE. PF as well as, so EF produced to the right. EF produced to the right. We have to cut L. Then since PF and the perpendicular PQ, PF and perpendicular PQ would both intersect L. Would both intersect L by the action of Pausch. So what is that? If EF is going to not be perpendicular to this, if EF is somehow going to intersect this thing, this means this EQ, if it's perpendicular, this means that from this construction, PF is so PB would also intersect. So this will also intersect L by the action of Pausch. So if this line is not assumed to be parallel, if it's not perpendicular, so if it's going to just intersect this thing, the corresponding lines are also going to get this line will also intersect this line will also intersect this line will also, so this is, you can follow it. So if we start with the perpendicular PQ from P to L, we start from perpendicular PQ from P to L and allows PQ. Now we're coming back to the what I should say diagram of Lobachevsky. So from this given point, if we rotate this plane, so it cuts lines into two parts. The lines, if you rotate this plane, there are some lines which after rotation of along a plane, they are going to intersect this line, and there can be some lines which may not intersect this line after this rotation. So this plane line cuts these lines into two lines. Ones those intersect this line, and the other which don't intersect this line. So which have a sort of reminiscence or analogy to that of how we study Dedekind's cut. A number line cuts a real line into two parts, rationals or irrationals. So the cut point which cuts the dense number line into rationals or irrationals, or one part into another part, we can have that reminiscent analogy to understand the lines which are going to cut and intersect this line, and lines which don't intersect. So if I borrow the words of this book, what he is saying is that if one starts with a particular PQ from P to L and allows PQ to rotate about P in either direction, you can rotate P in clockwise or counterclockwise to intersect L, while and then cease to intersect it. So what am I saying? So either it will intersect it or it's not going to intersect it. Either it will cease to intersect it or either it will intersect it. So the two bifurcations of two sets which cut line and which do not cut the line. First set, so the analogy is similar to that of Dedekind. So now, what's the point? The point which I want to emphasize, or which to emphasize, is that since the line itself either cuts L or does not cut it, it must either lose the lines which is, so it must, if either it cuts it or it does not cut. Another point, what's the point? But there is no last cutting line. But there is no last cutting line. So if it cuts it, so this line is not going to cut it. So you can have increasing number of lines which are going to cut it. So at the end, some line of it may not cut it. That's the point. So 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 that's the point. So there is no. It must either be that the last of the lines which intersect L or the first of those we do not. But there is no last cutting line. But for if one assumes that PG is the last of the cutting line, if one assumes, for example, that this line PG is the last of the cutting line, so this means, and measures of any distance GH, measures of any distance GH on the side G opposite to Q, then PH is cutting a line and a contradiction has been reached. So if you assume that PG is one of the lines, so it means that we are reaching a contradiction, that one of the lines will cut it. So if you assume that it cuts it, so it will contradict that it will contradict this line that it's going to. So if one of the lines is not, so we have broken it into lines which cut it and lines which don't cut it. And the lines which don't cut it, they'll be after the lines which cut them, and they will be they can be infinitely possible. Or the lines which will cut it will precede or succeed the lines, infinitely many lines which do not cut it. So if it really cuts it, so it will just somehow lead to contradiction, in the sense that there cannot be as many lines which will cut it at a point, because some line will cut it at this point. So that barrier of infinity, if my understanding is somehow it leads to that contradiction. So a similar situation is encountered if PQ is so it's counter. We have rotated PQ counterclockwise. If you do it clockwise, you can reach to the same conclusion. Hence, that is dividing line first of the a similar situation is encountered if PQ is rotated clockwise. Thus, there are two lines. Two lines, PR and PS through P, which do not cut L, which do not cut L, which are such that every line through P lying within the RPS does not cut L, such that there are two lines PR and RS. So there are two lines PR and PR. Thus there are two lines PR and PS, PR and PS through P, which do not cut L, and which are such that every line through P lying within the angle RPS does cut L. Lying between the angle RPS. So you can have, if you assume that there are equiangular, so there's this line RP and PS. So it's not going to cut this line L. But below this line, you can imagine lines like this J and this and this, which is going to cut this line L. Furthermore, angles RPQ and SPQ are equal. RPQ. So we had a start of the assumed that they can be constructed equiangular angles. RPS, RPQ, RPQ, this angle. So RPQ and PQS. PQS. So this angle and this angle RPQ and PQS are equal. If they are not, one of them is greater, say RPQ. So if they are not equal, for example, they are equiangular angles. If you assume that they are not equal, say for example RPQ or PQ, major angles IPQ equal to SPQ. IPQ equivalent to SPQ, IPQ, SPQ, IPQ. If they are not, one of them is greater than all. Measure that IPQ is equal to SPQ. Your PI will cut I in the point J. In the point J. So the point of this thing is that if you assume that one of the angles, these two angles are not equal. So one of the angles is they are not equal, less than this. So this will lead to some sort of contradiction. The contradiction will be of the form that PS does not intersect L. So if you assume that they are not angles, so you will not be able to form a congruent triangle. This means PS will not be is not going to does not intersect L. So this will lead to sort of contradictions. One concludes that angle this are this equal, or PQ is equivalent to SPQ. So from this we can have conclusion, or this angle RPQ is equivalent to SPQ. So the point is that you can construct parallel lines which can be equiangular from the both sides, and if they are not equiangular, they are perpendicular, you could reach to the Euclidean postulate that through a given point you can draw one parallel line through a given point. So otherwise these equiangular constructions will lead to successively parallel lines, infinitely many parallel lines having angle less than this angle, which are going to the other angles are going to intersect this thing. So the point, the convoluted argument is, consequently there will be lines through P within the angle RPS. So again otherwise you will reach to a contradiction. Contradiction is that there will be lines through P within the angle RPS, or PS within the angle RPS, we do not cut L under these sum. Again a contradiction. So otherwise you will reach to a point, there will be lines within this angle which will not cut this line. So again this sort of contradiction is reached. So this is not entirely maybe clear. Some sort of the proof is bit you need to mull over it or more, ponder over it or more to get grips of the proof. So the construction seems to be very much easy. And if you go to the book, there is a theorem which follows that. So if I am going to read that theorem, if L is any point on in any point not on L, there are always two lines through P which do not intersect I, which make equal acute angles with perpendicular from P to I, and which are such that every line through P lying within the angle continuum intersects I, while every other does not. So if L is any line and P is any point not on L, then there are always two lines through P which do not intersect I, which make equal acute angles, which make, so there can be always two lines which make equal acute angles with a perpendicular P to I, which are such that every line through P lying within the equivalent containing perpendicular intersects I, while every other line through P does not. So that's it. Now to illustrate this point, so there's a proof to this point. So there can be further theorems. So this statement of this theorem was in the context of the previous theorem, which we tried to previous statement of this thing, how we arrived at it, and in that sense that all of the lines through P which do not meet L are parallel to L from the Euclid point of Euclid. From the Euclid point of Euclid, they are parallel. So now, what are the properties of the elementary properties of the parallels? So normally in the traditional construction of parallels is that through a given point only one line can meet one, and never no two parallels can meet. But it's not necessarily the parallels will be parallels in that sense. They may seem to be intersect, they may seem as if they are not parallel if you see through the Euclidean eye, but if you can extend them, they will still not meet at any point. They are still parallel. So if there's a theorem to that construction, for example, if we have this diagram like two lines A, L, this is P, so we assume that these two lines are also parallel. So if you assume P or B, this is S, and this is point N, this is U, this is T, this is S. This is M. So if a straight line is parallel through a given point in a given sense to a given line, it is at each of these points that are parallel in the given sense to the. So I'll not prove it. So there is enough. In the same way, there can be another diagram. So this is if the theorem is if straight line is parallel through a given point in a given sense to a given line. At each of its points, the parallels in the given sense to the given line. This is one theorem, so I'll not. So the theorem 2 states that if one line is parallel to second, then second is parallel to the first. Second is parallel to the first. So if one line is parallel to the second, second is parallel to the first. So it's also in construction. It needs some amount of thinking to absorb it. So let me just the third construction. This construction maybe is this construction is more helpful. So if I just draw it at theorem 3, I'll try to just see it how much we can. So if we have 3 lines, so which are parallel not in the Euclidean sense, but from a non-Euclidean sense. So if there are 3 lines, and so this is this point, and so this is point I, this is G, and this is E. So this is this is E, this is G, and so you can have you can have this point C. So what's the theorem? So I'm going to state the theorem. Theorem states if two lines are if two lines are both parallel to third line, if two lines are parallel to the third line, or this line is parallel to this line, or these lines are parallel to this line, so any of the thing which you can imagine of, if two lines are both parallel to the third line in the same direction, then they are parallel to each other. Even though we know it from a Euclidean sense, they are parallel to each other. We are trying to prove the argument in the if assumedly these lines are not Euclidean lines. We are not working with the Euclidean prejudice. Still, can we show that they can be parallel to each other? So we are trying to verify our prior conceptual belief of Euclidean statement. If two lines are parallel in the Euclidean sense, they are parallel to the third line. They are parallel to each other. So if you assume that two lines not so if you don't assume that way, it will lead to some contradictions, and which we are going to see how it will lead to that sort of contradiction if you don't assume the statement for in these lines. So this is the point. So let AB, this AB and CD both be parallel to EF. So AB and CD is parallel to EF. That's fine. In the same direction. Third, CD be parallel to EF in the same direction. And let AC cut EF at G. So let AC. So AC cuts EF at point G. So you can so it cuts line EF at point G. So this is fine. Draw any line AH through A passing. Draw any line AH. Draw any line AH. So we are drawing any line AH through A and passing with an angle CAB. That's fine. So from this angle CAB, from the vertex we draw this segment H. The line will cut EF in the point I. So that's fine. The line will cut EF in the point I. So we have just constructed a line, so it will cut. That's fine. So draw CI. That's fine. Since EF is parallel to CD, that's fine. EF is parallel to CD. But every line through A, lying within the angle CAB does. Every line through A, lying within the angle CAB, does that. It follows that AB and CD are parallel. AB and CD are parallel. That's fine. So if AB is not, if you assume that AB and D are parallel, but if you assume that AB cuts this line, then it's also cuts this line from, just like we have in two parallel lines. If two lines are parallel to each other, they cut one of the lines which is parallel to either of the two. It will also cut the other line. So you can, if you can draw one of the lines from this. If it's going to cut this line, it's also going to cut this line. So it assumes that. So this means that AB, and so this is simple argument. Now next is that consider the case in which two lines are on the same side of the third, and let AB and CD both be parallel to EF in the same direction. That's fine. Assume AB is not parallel to CD. Yeah, so we assume that AB is not parallel to CD. In that it is now we have proved by contradiction. We assume that AB is not is not parallel to then through any point G of AB, through any point G of through any point G of AB, draw or we draw the parallel GH to the CD. So we can draw GH. We can draw GH parallel to CD. We can draw GH parallel to CD. We can draw GH parallel to CD in the designated direction. Then through any point G of AB, draw parallel GH in that direction. GH parallel to CD. GH parallel to CD in that direction. It follows in the first that GH is parallel to EF and GH is parallel to EF. GH is parallel to EF. But only one parallel in that direction can be drawn F through G. So it assumes that therefore G must H must coincide with AB. So the proof hinges on only one simple fact that we cannot construct a parallel from this point which is parallel to D. Only one line, one and only one line can be drawn, which is parallel to this CD, which should coincide with this thing. So the proof hinges on this point, simple fact. Otherwise, it should lead to contradiction. So if you beautifully has shown diagrammatically, if you try to imagine it diagrammatically, so you assume a line B, and you assume that there is another line H. So, which is a G. So assume a line A, B, H. So you cannot assume that this is a line which is intersecting it. You can have this is another line which is being constructed from this point. So there is another line CD. CD. Another line EF. This is this. This is this. So this is this. So we can construct. This is for the exemplification of this thing. Stop at this point and further continue with the fact. Continue with this discussion. Modulo that the exercise I did not prove. So there is an exercise in the book. For example, if two lines B and BC are both parallel to line L, show that the bisector of angle ABC is perpendicular to L. So the exercise says that BA and BC are parallel. BA and BC are both parallel to L. So BA and BC, BA and BC are both parallel to L. So that bisector of the angle ABC, bisector of the angle ABC. So you can have this thing, bisector angle BC is perpendicular to L. So if an angle is going to bisect this thing, BAC, if BA and BC are parallel to the line L, parallel to the line L, if you zoom it like this, so bisector of ABC, bisector of ABC. So something is AC is perpendicular to L. It should be, so you have to prove it is perpendicular to L. So it's a simple exercise. So in the same way, there are other two theorems which I did not see. If one line is parallel to the second is parallel to the first. And so these are simple argumentation he has given, which we can understand after some amount of a bit of concentration is required so to make things clear. So I'll stop and continue.